black holes glow now.
Yes. Yeah. So now we're going to get into this. So, this is out of University of Amsterdam. Physicists there, they simulated a black hole in the lab. And this was to test Stephen Hawking's theory that black holes emit radiation, known as, surprise, surprise, Hawking radiation. So what they did was they created an analog of a black hole's event horizon, which is um, the boundary beyond which events can't affect an observer. So when they did that, they surprisingly their simulated black hole started glowing, which could be indicative of Hawking radiation. And just to get into a little bit, Hawking radiation, it's believed to occur when particle antiparticle pairs are generated at the event horizon with one particle escaping. And the glow in this experiment only happened when part of the experiment simulated curved space-time due to gravity, which supports the quantum basis of Hawking's theory. So just I know it's a lot. That the breakthrough, what it does is it allows researchers to study elusive black hole properties using lab simulations. So they're able to kind of push their understanding and advance their knowledge.
Okay, so we talked about black holes a minute ago, and so the first thing we learn about black holes is light doesn't escape black holes. So how do we detect this glowing radiation?
So now, yeah, that's cool. So, um, Hawking, that's a good question. How do we detect it?
Sorry.
Um, I don't know how they detected it. I didn't see that in the article. I should have done a deeper dive, but I'm not sure.
No velocity,
I
no
know it's a
meters can manage to
phenomenon.
escape
Yeah,
being sucked in, not even traveling beyond light speed. So which is great. But how do you detect this glow? I guess because it's a simulation in the lab.
yeah, and we can get into that how they simulated that. So what they did was they simulated a black hole in the lab by creating an analog that exhibited some of the key properties of an event horizon. So creating an analog in relation to a black hole creation, what it means by it, you're constructing a system that mimics some of the important properties of a black hole without actually creating a black hole. So just so you know, they haven't actually created a black hole. What they're doing is they're aiming to reproduce some of the features of the black hole, like we just talked about, event horizon, and Hawking radiation in a small experimental setup. It's done by manipulating exotic states of matter or engineered devices to imitate gravitational space-time warping. So, for example, using sound waves in a fluid to model an acoustic horizon or laser light, like we were talking about before, in optical fiber, which represents a photonic event horizon. So that's why I wasn't able to answer your question, because they're not actually creating a black hole, right? And so um, detecting it from a black hole kind of threw me, because I don't know how you would detect it regardless. So, but analog models, what they do is they allow phenomenon like Hawking radiation to be studied in a controlled lab environment versus observing black holes. Now, the thing is it's only replicating limited aspects of a black hole's physics. But what it does is it provides insights on the underlying quantum processes. So we're getting into quantum again. All this stuff, guys, most of the stuff that we talk about future tech that's really advanced, it all is derived or all comes back to quantum properties, quantum mechanics, quantum physics, things like that. So when we're talking about things like this, it does go beyond. You have to, again, and I repeat this every time quantum comes up, but you have to throw out all of your understanding of physics and things like that as you know it today. um so yeah, so what it does, so a black hole analog uses innovative techniques which we talked about to mimic black hole behavior in a small system. It doesn't create a black hole, it creates similar effects to the black hole, if that makes sense, similar properties.
Yeah, and it's suggesting that this may be due to some sort of quantum entanglement, like you were mentioning,
Yeah.
so that quantum entanglement may not be affected by radiation? By
Yeah.
radiation, sorry, by, gravity?
Well, yeah, and that's if you think about the concept of quantum entanglement, right? Quantum entanglement means that there's two particles that exhibit the same properties at the same time, right? Until you observe it. So that could make sense, but again, this we're talking like super advanced tech at this point.
Yeah, so they're talking about, what are some of the potential applications of simulating black holes in labs? And I always like to say that, we talk about simulations and computer models, and computer models they're all wrong,
Yeah,
but some of them are valuable. So we just have to take a step back. Some people just say, oh, computer models. Well, that was just some guy programming a bunch of stuff into a spreadsheet and running a simulation.
yeah.
So, you know, it's great that we can advance stuff, but I'm not 100% sure that the results of everything will be real. But what are sub potential applications of this breakthrough?
Yeah, this is cool though because obviously we talked about you could investigate the Hawking radiation properties. Um, so you could develop new detection methods, which could help guide the development of instruments and techniques to detect the Hawking radiation from actual black holes because there's no way to do it right now, right? Um, so it could validate the existence. Um, Testing the quantum entanglement and information paradoxes. So, black hole simulations may allow for testing quantum effects like entanglement across the event horizons, which could provide insights into information paradoxes. Um, so, investigating other space time geometries, so other exotic space time geometries beyond black holes could be simulated and studied. Developing materials with unique properties. So, the extreme gravitational analog environment could potentially lead to these huge breakthroughs of development of materials with novel mechanical, optical, or quantum properties. That's the one that I'm most excited about because that one is the one that I see as the most practical for um, for us right now, if that makes sense. Like black holes, to me, they're great. They're really interesting. I'd love to be sucked into one, um, but it's so hard to observe, to measure, to do a whole bunch of things with actual black holes. So by taking the theories of the lab stuff and be able to use that to develop materials, new materials with new types of properties, that's really cool to me.
So you talked about the black hole information paradox. What is that?
So the black hole that's a good question.
Just so
You
while
were
you're
testing
just,
me this morning after a late night too. So
I know I hate to ask these tough questions. I keep you out
yeah,
to
so
midnight.
it's a theoretical problem that's highlighting the apparent contradictions between quantum mechanics and relativity around black holes. So according to quantum mechanics, physical information about the state of a system should never be destroyed. But black holes are predicted to completely evaporate over time. And that's kind of getting into Hawking radiation. So it suggests that any matter or information swallowed by the black hole will be lost forever once the black hole fully evaporates. So the thing is this violates quantum, some sort of quantum thing. I can't remember. On the other hand, general relativity says that information should always be conserved according to the laws of physics. So it contradicts conclusions from quantum theory. So it remains a question of what happens to information swallowed by black holes, right? So it remains a huge mystery of the fundamental of physics, essentially.
So it's just another example of how physics is real physics and quantum physics is magic.
I knew you were getting there. Yes.
All right. So they're simulating black holes. Are they actually trying to create a black hole? And should we be worried about that they're going to destroy all of us because, oops, I just created a black hole and now we're all gone?
Yeah, so I don't think there's a need to worry that black holes created in the lab could become dangerous or uncontrolled, and I'll explain for a few reasons. So first off, the thing, and we're going back to what I already explained, but the lab only mimics properties of black holes, so they don't contain anywhere near the mass or gravitational pull to actually become a black hole. At most, they recreate the space-time warping effect. So the other thing is they're using specialized metamaterials and nanostructures to create the analog effects, which I don't know any information about. But if these were disrupted, the black hole like effects would immediately disappear. The other thing too is the experiments operate at microscopic scales using photons, sound waves, or electrical currents. So there's really at that scale, there's no chance for an uncontrolled growth based on what they're doing right now. Um, the other thing too is the researchers have full access to tune and turn off the equipment generating the simulations. Um, and then there's lab safety standards, but you never know, right? With lab safety standards, that one doesn't really put me at ease. But more of the that they're mimicking only some of the properties, that more puts me at ease. So um,
The
the
mimicking puts
reality.
me at
Oh,
ease rather
what's
than the
that?
other stuff. The mimicking puts me at ease. That other stuff doesn't, because the other stuff
No.
sounds like, every classic sci-fi horror story. Well, we put all the stuff in place,
Yeah,
but
exactly.
black holes power themselves.
Yeah,
They don't need once they start they don't need you or machine turned on to continue. They just continue by sucking everything in and increasing their power by that.
yeah, exactly.
So
Yeah. So
it,
yeah,
it
the only thing that really puts me at ease is that they're only mimicking. Everything else doesn't really put me at ease. But I guess it's nice fluff. Yeah.
So one last question before we see what's happening in everyone's lives here is, all right, is this going to lead to bigger advancements in quantum computing, and or is quantum computing going to be is this what the $5 million answer that quantum computing can solve is time travel?
It's a good question. But because there's so much quantum physics tied to black holes, that could potentially lead to advancements in quantum computing in a few ways. So, testing quantum gravity theories, uh, black hole simulations could serve as a platform for testing theories that aim to unify quantum mechanics and gravity, such as loop quantum gravity, which often make predictions relevant for quantum information science. And I didn't do a deep dive into kind of what the advancements actually mean. I just came up with a list of different things. So, um, developing qubits. So, some proposed qubits implementations they rely on artificial analogs of event horizons to isolate quantum information. So, the techniques in these simulations could inform quantum computing platforms, which is really cool. And then exploring quantum advantages, which we talked about before. So, simulating gravitational systems may offer us a route to explore quantum advantage on controllable analog quantum computers before fully scalable ones are built. So, there's a lot of work that remains, but the field of artificial black hole simulation could provide a really great testing ground for developing ideas and technology relevant to quantum computers for sure.
Yeah, and I want to get a couple of Canadian quantum computing
Yeah.
founders in just to talk about some stuff, like I said, but that might take a month or two to coordinate everything. Any final words on this? I mean, this is really cool. I'm just curious as to where we're going.
Yeah, no real thoughts. These are really advanced concepts, and that's why I didn't have as many of the answers that I normally have, because when we're talking this advanced kind of tech, it's a lot to grasp. Especially me just being a software engineer and not a quantum physicist. But um, I think there's some really cool technology. Again, we're all most of this stuff is theoretical except for the reverse microwave, but a lot of the stuff we talk about is theoretical, guys. So there's really not much that is proven yet. Think about, for those of you that think about the Big Bang Theory, the work that Sheldon does. It's all theoretical work, right? So it's the stuff that we talk about is stuff like that.
Thanks for all the information. Um, we know that you work with tech companies to help them get government funding and navigate the fun world of being a startup here in Canada.
Yeah.
Um, Anything you want to add to that, and where can people go find out more if they have questions about funding and want to talk to you?
Yeah, thanks. Yeah, send me a message on LinkedIn. Find me on LinkedIn. Very easy. John Irwin, no H. Um, and I'm happy to have a discussion. Happy Craig and I work very closely together. So if there's something that I feel Craig might work better with you on, I'll definitely pass them your way. But if you have any questions on non-dilutive government funding, hiring grants, training grants, shred any tax credits or any kind of grants, feel free to reach out to me.
And if any of you listening, the audio or video is breaking up, we do separate local recordings. It takes a while to come out, but the audio will be pushed out on the podcast. We push it out. We're about 2 weeks behind our the when the podcasts come out. We're just from the timeline point of view, but we'll get great audio and stuff there.
Okay.
Check out all of our stuff. We help entrepreneurs. We do events. We were just talking about last night. We were at Startup Drinks TO. We were a CIX after party. We had 100 people out. There was about 20 investors in the room. It was a great time. It's open pitch, open bar. Check out startupdrinksto.com. The next one will be April 25th, and that'll be posted by the time you're seeing this. I work with startups all the time. If you're stuck in your business and you don't know where to go and you want to move forward and you're frustrated, book a discovery call. Go to startupcoach.ca. It's absolutely free. We can chat about how I can help you and how to get unstuck and actually turn your business into a profitable, successful, and a happy place for you to work. Check out our stuff at TorontoStarts.com. Thanks for watching us today.